what quantum computing is all about is we're trying to do computation on qubits, but on practice there are many different ways to realize them experimentally. You can do it with superconducting qubits, ion traps, or neutral atoms, and they all have their own distinct constraints and also different properties. So what sys-sage focuses on is it tries to characterize the individual properties and also constraints such that we can leverage them while doing our quantum computation.
This particular paper was actually the result of Drugansh's master's thesis, and Martin was his examiner and Stepan and I were his supervisors. So basically our role as supervisors was simply to make sure that the methodology is sound, it's accurate, and it's implemented in a robust way.
Together with the TUM team, we collaborate quite tightly, so we kind of know each other and we know what each individual is working on. So while we started working on this project, we know each one of our strengths, so we could easily distribute the tasks. For instance, Xiaolong had the experimental background within the lab, so he knows more about qubit characterization. I, on the other hand, have more expertise on quantum algorithms and on the hybrid, let's say, the higher abstraction levels. So we found very nice synergies while distributing the work. The Munich Quantum Software Stack is a huge project. It starts with the quantum computing access, so it basically gives users the access using either Pythonic accesses or HPCQC accesses, and then it continues with the quantum compilation tools, and it ends up being basically routing the quantum algorithms to the specific quantum hardwares. And sys-sage would be a module as an intermediate part, and it will help us to schedule quantum jobs to the best possible quantum hardware for instance.
The sys-sage dynamically monitors the behaviors or performance of QPUs. So it can observe the different qualities or fidelities of qubits, and then it will collect it. As soon as there is application or job sent to HPC or sent to QC, it will recognize it, which QPU is good for which job. Then in this sense, it will optimize the applications by sys-sage.
ISC is arguably the most important event in HPC in Europe, and winning the Hans Meuer Award is not only addressing our efforts, it's also helping us disseminate our Munich Quantum Software Stack.
At least the goal is to prepare a complete software stack. So the capabilities start with giving users the access, and then it basically handles everything that a user doesn't need to do. For instance, it will optimize your quantum circuits for you. It will try to reduce the complexity of the circuit such that the circuit will not get affected by the noise of the system. And then it can schedule the quantum job for you, so it can select the best possible quantum backend for you, and then many other steps in between.
The Munich Quantum Software Stack is open source. You can literally visit our repositories, clone the entire code base, and start running your own experiments. Currently, we haven't made everything public yet, because in order to make it public, you need to have documentation, proper tests in place, and so on. We're working on that. What we're doing is to make public pieces of the stack little by little. Currently, I would say the most mature piece of the stack is our interface, the Quantum Device Management Interface, or QDMI, which is public right now, and we always ask people to contribute, to give us our feedback. People can create so-called issues, conversations, and let us know what else could be required for such a system. And quantum computers will never replace classical computers. There are problems that quantum computers cannot even solve that classical computers can. But like I said, the problems quantum computers can solve are incredibly relevant.